All right. Let's go over example 3. I'll do a quick review. Hope students saw the announcement and I had time to go over the video and the slide. Since it was in the class notebook, all students who have access, well, all students who signed up for the class notebook would automatically have received it at their end. So let's go ahead and do that. Just as an FYI, almost 90% of the previous 2 sections didn't check the announcement or didn't check the video. So they had no idea. All right, let's see. Okay, equivalent circuits, example 3. We are asked to find the Thevenin and Norton equivalent circuits if the 17 ohm resistor represents the load network. And as always, whenever you see the word as seen by or represents the load resistance or represents the second circuit, that component is no longer part of your analysis. So we remove that and we redraw the circuit. Now, this drawing right here is simply for explanation purposes. Students do not have to redraw the circuit diagram. Okay, this is just for explanation. It's just to show that the 17 ohm resistor is not part of the analysis and the terminals are open. Okay, so terminals are open. We analyze between terminals A and B, and we analyze 3 separate times: VTH, RTH, and IN. Thevenin voltage, Thevenin resistance, and the Norton current. So let's draw the circuit diagram for the first one. Thevenin resistance. For Thevenin resistance, in real life, obviously, it's easy to measure the voltage, current, and the resistance. All we do is we take our meter and we connect it to the output terminals A and B. And we can measure resistance directly. We can measure the voltage, and then we can measure the current, all within 30 seconds. All right. For calculations, of course, it takes longer. RTH is measured between terminals A and B. We find RTH by calculating REQ for that network. In order to calculate REQ, we reduce all independent sources in the circuit to 0. Reducing a source to 0 means reducing or replacing the voltage source with a short circuit and replacing a current source with an open circuit. So voltage source is a short and current source is open. Redrawing the circuit, I am only left with 3 resistors for my REQ. I can see that the 5 ohm resistor is in parallel with 20, which is then in series with 10. And so I have my REQ as 14 ohms. Thevenin resistance is REQ of the circuit, ends up being 14 ohms. Okay. Again, more than the calculations, it is important to do the problem setup. Okay, the analysis techniques are not new. Again, Thevenin and Norton does not require learning any new analysis technique. Everything that we learned in chapter 2 so far is applied in Thevenin and Norton theorems. But students have, it's new concept that requires a lot of application. And so students need to understand that, again, problem setup is more important. Okay, analysis techniques come later. All right, any questions? We took our original circuit. We measured REQ by reducing all independent sources to 0 between our terminals A and B. Okay, that gives us our Thevenin resistance. All right, then let's go to Thevenin voltage. In Thevenin voltage, We go back to our circuit. We're analyzing with all the sources active at the same time, but our output terminals are kept open. Obviously, we need to measure the voltage between those terminals. 17 ohm resistor is not part of our analysis. We simply analyze the circuit to find the voltage between the open terminals of A and B. Okay. Hence, we call it open circuit voltage, VOC, and VOC is measured between A and B. Now, to find this voltage, you can use node voltage analysis, you can use mesh current analysis, or you could use superposition. It does not really matter what you choose. Okay. Now, in the exam, I would have specific method stated in the problem statement itself. So if a specific method is stated, then you have to use that particular method. You cannot use anything else. Here, you can choose MCA, NVA, or superposition. I chose node voltage analysis this time. In previous years, I've actually solved this using superposition. You still get the exact same answer, no difference. One segue, one side point, when trying to decide between node voltage or mesh current, you want to look at how many unknown variables you have to solve.
Or there, 1, 2,
6. Okay.
Yeah.
I'll work on these two.
So you want to see, you want to see, I lost my chain of thought. Okay, when trying to decide between mesh current and node voltage, you want to look at the unknown variables that you're trying to solve. For mesh current analysis, it is the number of meshes. For node voltage analysis, it's the number of nodes. In this case, I can see I only have 2 meshes, one here and one here. So 2 unknown variables. And even in that upper mesh, which has the 1.5 amp source, if I choose my mesh current in the exact same direction, I automatically have an answer for that mesh. So the only unknown variable would be in mesh 1. Trying to solve that. Make sense? Right? However, if you look at node voltage analysis, we have 4 nodes. We have the bottom node right here, B. Then you have node A, which is right here. You have node C, and you have node D. Remember, node is any point in a circuit which has 2 or more components coming together. If you don't have 2 components at that particular node, at that particular junction, then it is not a node. It is not a separate node. It's the exact same node. A wire, as you look at the bottom node B, can be as long as it wants, but it still is one single node. Okay, so in this case, I have 2 nodes A and B marked out in the problem itself. And I'm just going to take the other 2 nodes. I'm going to note them as node C and D. Okay, node C and D. We can call it X and Y, L and M, doesn't really matter. It's all the same. It's just notations. So I chose C and D just to be consistent. So I have nodes A, B, C, D. But I also have a voltage source. And it just so happens that the voltage source negative end is connected to B, which is the place where I wish to measure my node A voltage. So coincidentally, it just happens that the voltage source is connected there. So if I choose node B as my reference, which I've done here, I automatically have the answer for VB, which is 0 volts. And then I also have an answer for node C, which is 20 volts. And VOC is measured at A with reference to B. So if I choose B as my reference for the analysis, I also know, or I conclude, that VOC, my open circuit voltage, is VA, the node voltage VA. And that gives me an advantage, or actually simplifies my circuit. Make sense? Right? So out of 4 nodes, A, B, C, D, I eliminated B by choosing it as a reference node. So that's 0 volts. and then automatically gives me VC as 20. So I have two unknown variables, right? Two unknown variables. Now all I have to do is assign branch currents. So I've assigned 4 branch currents, right? The current that flows through every branch, and then I apply KCL at the node. Logically, my 20-volt source has current going from minus to plus, so it goes up. It enters the 5 ohm resistor from the left, and so my branch current I1 is noted as going towards the right. Then I have the 1.5 amp current source. So that current goes in this direction. And then it comes around and enters the 10 ohm resistor from the right. And so I chose I3 flowing through the 10 ohm resistor as going towards the left. And then, of course, I2 I chose as going down. So if I apply KCL at node D, I have 4 currents right there. 2 of them are entering, and 2 of them are entering and 2 of them are leaving. I put both of them equal to each other, and I have my KCL expression. I1 plus I3 is equal to I2 plus 1.5. Okay. Now simply solve that equation. I3, of course, is 1.5 amps. Eliminate that. I have I1 equal to I2. Apply Ohm's law. Express each branch current in terms of the node voltages. Oh, not there. Sorry, here. Node voltages. So I1 is VC minus VD, and here I2 is VD minus VB. If we look at the circuit, I1 is going from the left, so C minus D, and then one more, and then I have I2, which is D minus B, and B, of course, is a reference point, so that is equal to 0. I end up with 4VC minus 4VD equals to VD, and that gives me VD equal to 16 volts. Remember, VC already has a value of 20 volts because B is a reference node. So you solve that, you obtain node at voltage at node D as 16 volts. Then I need to find a value for node A. I simply pick an equation which has node A in it, which would be I3. Plug in the value for VD, and I obtain my answer at A as 31 volts. Let's take a 10-second pause while you write that down. Again, this is the node voltage analysis simply to find the Thevenin voltage. Okay. It has no bearing whatsoever on the mesh current analysis or the Thevenin resistance. All right, any questions? Any questions at all? I mentioned in the past, I've solved this using superposition, right? So it requires 2 separate analyses just for that one voltage quantity, right? Just for that one voltage quantity. I'll quickly show you that if you're trying to do the superposition, this would be 0. 1.5 amps goes to 10 ohms, and you would get 15 volts. 15 volts. And then when you analyze for the 20 volt source, you would get 16 volts. 15 plus 16 would give you 31 volts, which is what we found using node voltage analysis. Okay. So again, no matter which method you choose, if you choose mesh current analysis, which actually I'm interested to actually solve this. I've never done that using mesh current. I'll do that this afternoon. If you solve it using mesh current analysis, you would still end up with 31 volts. You should. And it's a good way to practice. All right, any questions? Any questions at all? Okay. All right, then moving on to find a short circuit current. Well, not short circuit. So moving on to find the Norton current for this circuit. Current needs a pathway to flow through. So we place a short between terminals A and B. That short circuit current, ISC, is my Norton current. Because of that short circuit, I now have a third mesh in my circuit. And I label those meshes as M1, M2, and M3 with mesh currents I1, I2, and I3. Again, you can choose node voltage for this analysis also, or you can use superposition. It's all the same. Two observations at the top. Mesh current I3 has the same value as the 1.5 amp source. So I3 is 1.5 amps. Short circuit current ISC is equal to I2. Okay, short circuit current ISC is the mesh current I2. All right, so I'm going to apply KVL in mesh 1 and mesh 2. In mesh 1, I have 3 voltage drops, the 20 volt source, and the 5 ohm resistor, and the 20 ohm resistor. Okay. And then, again, a note about mesh current analysis. Choose clockwise direction for every single mesh current. And when you do that, when you write out the KVL, if you're writing the equation for that particular mesh, the current for that mesh will be positive. All other currents outside the mesh will be negative. And so I1 is positive because I'm writing the equation for mesh 1, and then I2 is negative. Plug in the values, reduce it to a linear shape, linear form, and I get 5I1 minus 4I2 equals 4. I will label that as equation 1. Then I apply KVL to mesh 2. I have only 2 resistors in mesh 2, 20 ohms and 10 ohms. But both of them are shared. But since I'm in mesh 2, I2 is positive, and then I1 is negative, and so is I3. Make sense? Again, plug in the values, reduce it, and you get minus 20I plus 30I2 equals 15. I will label that as equation 2. Once you have a set of linear equations, you solve it with any method you want. Okay, plug it into your calculators. If you can program them, it will directly give you values, but you need to be an expert at using your own devices. I would not be able to help you with that. Again, at this point, it's simple high school algebra. Simply find the values for those equations. In the exam, I will not give you anything that will have more than 3 variables. Okay, but again, you can set up a matrix, solve using determinants, and again, not too difficult. Yes. Yes. Yeah. Yeah. So most likely it'll be 2, but definitely won't be more than 3. So the way I would do it, I would set maybe the last couple of weeks of class, typically the last week of class, I start designing problems. And once I design a problem, I solve it. And I take a look at how long it takes me to solve it. And then based off of those calculations and past year's experience, I estimate how long it takes students to solve this. And if it doesn't work, then I go back and redesign it again. Anyway, so we solved this and we obtained ISC, or short circuit current, or Norton current, as 2.2142. All right, 2.2142. Yeah. And then, of course, we apply Ohm's law to verify our answers. If, of course, Ohm's law doesn't work, then there's an error in our calculation somewhere. And then the final Thevenin and final Norton circuits. Now, quick point about these circuits. The circuits are the same for every single circuit, right? Every single problem will have the same end result. The circuits do not change. Think back to the beginning. The entire premise of this topic is that we have a large network of circuits, a large network of resistors and multiple sources, and we can represent it as one single voltage source and one single current source. So every circuit that we analyze will end up as having this as the final step. The only difference would be that the Thevenin voltage and the Norton current and the Thevenin resistance would be different. But the circuit diagram for the final Thevenin and final Norton will always be the same. And once you practice this and do the homework and do the quizzes, it should be, well, it should be very easy after that point. Okay. All right, take a 10-second pause. Let me know if you have any questions. Any questions at all? All right, then moving on, there are two final topics for chapter 2. Source transformation and maximum power transfer theorem. Now, source transformation is something, it's a topic I like to teach students, but I do not recommend you use it. And the reason is, it is a tricky, the concept is easy, but it's tricky to actually do it. Oftentimes I find myself trying to do this and I end up with the incorrect answer. So I definitely, I always tell students that, okay, it's easy to understand, it's easy to, but it's not easy to do, not easy to implement. Okay. The concept comes from the equivalent circuits of Thevenin and Norton, right? Both theorems state that you could take a large linear network and represent it as a voltage source, or you could represent it as a current source, right? So if A equals X and A equals Y, I can conclude that X equals Y. If you think back, well, not think back, let's look back at the beginning of this topic. We had this large circuit, and I said, or I stated that we can represent it as a Thevenin network, or you could represent it as a Norton network. So if both things are equal, then I can say both of these are equivalent to each other. And that's where source transformation comes from. If a circuit can be represented as a Thevenin or a Norton network, then the Thevenin equivalent is also the same as the Norton equivalent. The only question is, not only question, but the only point is that the Thevenin resistance has to be included. Meaning, if you wish to transform a source from voltage to current or current to voltage, you need to have a resistor in series with the voltage source or a resistor in parallel with the current source, without which the conditions are not met and you cannot transform the source. Okay. And the equation, of course, that relates the two is V equals IR. A voltage source can be transformed to a current source using Ohm's law. Let's look at an example so it will make more sense. We have the circuit here in A. right? Two sources, 20 volts voltage source and 1 amp current source and two resistors. Simple as far as circuits go. But because there are two sources, if you wish to find the current I1, let's say, or the voltage VR1, you would have to at least do superposition at a minimum. Superposition, or you could do mesh current analysis or node voltage analysis, right? There's no other method. But source transformation would allow me to skip all of those steps and find the answer in only 2 steps. I'm going to show you how. What we do is we break up the circuit. At this point. So it's very important. This is where most of the errors happen. You break up the circuit and you're going to take whatever source you wish to transform, you're going to take it out of the circuit, you transform it, and then you plug it back in. So here, I'm going to take my current source and I wish to transform the current source, right? The first condition is that it should have a resistor in parallel with it. So I break away the circuit from a certain point. I transform it into a voltage source. And the voltage source should have a resistor in series, which is the same resistance as the 10 ohm. And the voltage is given by Ohm's law. So it's 1 amp times 10 ohms gives me 10 volts. And then I plug it back into the circuit and I obtain that. Oh, sorry. I obtained this. I had a current source, you broke it off at 2 points in the circuit, you took it out, you transformed it, and you plug it back into the same point. So the breaking is easy, but plugging it back into the circuit at the exact same 2 points, that is tricky. But now that we have this circuit, which is circuit B, what do we see? Previously, R1 and R2 were neither in series nor were they in parallel. What do we see now? They are both in series. And they're both in series. My circuit simply becomes like this. You don't even have to do a mathematical equation here. Voltage is nothing but the difference in potential between 2 points. So if 2 points in a circuit are exactly the same potential, answer is 0, right? 100 volts, 100 volts, 0 volts between those 2 points. What do we see with the resistor? Common reference point, negative ends of both power supply connected together. So this end I have 20, this end I have 10. What is the voltage across that resistor? But polarity, no, not polarity, but this end is 20, this end is 10. What is the difference between the 2 points? 10 volts. Which point is higher? So positive is here, negative is here. So plus minus, and I call this V15. Mathematically or quantitatively, if I wanted to write an equation, I would do a KVL around the loop. I have 3 voltages. I can write down minus 20 plus V15 plus 10 is equal to 0. V15 is 20 minus 10, 10 volts. Okay. That was just a concept, meaning that just comes after lots of practice. But mathematically, you can still apply KVL and you can get the answer. Yes. It's Ohm's law. Ohm's law relates the source transformation. And then another one-step answer is applying Ohm's law, and we can find I1. 10 volts by 15, 0.667 amps. So no superposition, no mesh current analysis, no node voltage analysis. You can find the answer in like 2 steps by doing a source transformation. Make sense? But it is tricky. If you had another circuit connection here, then we are breaking it on the left side. We're also breaking it on the right side. We take it out, we transform it, but then we try to put it back into the circuit. It won't work. It's a little tricky to put it back into the circuit. So you have to be very careful where you're breaking it. It helps if it is at one end of the circuit, right? So you only have to break it at one point, not at two. Right? We could also transform this into a current source. So if I was to take the voltage source, voltage source needs to have a resistor in series, which it does. I transform it into a current source. That current source will have a value of 20 divided by 5, which is equal to 4 amps. This would still be 5 ohms. And you plug it back into the circuit and you get 2 current sources together in the same direction. You can add them up and treat it as one single current source of 5 amps and solve the circuit that way. Okay. But again, easy as a concept, but difficult to implement or difficult to use if you want to use that. So it's not a technique I don't use it a lot. On occasion, just for kicks, if I'm trying to it's like solving a puzzle. So if I wished, sometimes I do it, but most of the times, if I'm trying to do an analysis, I will avoid using source transformation. Okay, but students should be aware of what it is and where it comes from. It comes from the equivalence of Thevenin and Norton equivalent circuits. All right, one last topic, one last slide, maximum power transfer. In electrical engineering, electric circuits, or in electronic circuits, we always have multiple circuits connected together, like a cascading series of circuits, like cascading steps. If circuit 1, the output of circuit 1 is connected to the input of circuit 2, and the output of circuit 2 is connected to the input of circuit 3. RL represents either a single load or it is the second or a succeeding follow-on circuit. So maximum power transfer theorem states, if you wish maximum power to be transferred from circuit 1 to circuit 2, the resistance of circuit 2 should be equal to the Thevenin resistance of circuit 1. Essentially, the Thevenin resistance of both circuits should be exactly the same. Okay. I should note, maximum power does not mean maximum efficiency. Okay, maximum power is not transferred at maximum efficiency. It's very different. So sometimes you want efficiency, sometimes you want maximum power. A real life example is your audio system, audio speakers. Audio speakers are connected to the output of an amplifier. Internally, the amplifier is connected to a preamplifier. You say, you have preamps. More likely, you might have heard as guitar amplifier or guitar preamp. So you have a preamplifier stage that filters out unwanted noise signals and unwanted signals, basically. It takes your incoming signal, either from your Blu-ray player, from your TV, from your computer, from your guitar, strengthens it, gives it to the amplifier, and the amplifier sends it to your speaker. If you go online and check out the specs or the spec sheet for any speaker or any speaker box for that matter, it'll state 8 ohm impedance. Impedance is something we'll look at when we get to AC analysis, but think of it as resistance for now. So the speaker will have a spec which says 8 ohm resistance. It means you connect that speaker only to an amplifier that has a output resistance of 8 ohms. If you go online, you can check out the PDF manual for any audio video receiver or an amplifier. It will always have a spec that says 100 watts, 2 channels into 8 ohms. Okay, it means you should connect an 8 ohm speaker to that particular amplifier. If you connect a 4 ohm speaker to an 8 ohm amplifier, it's going to supply a whole lot more current that it needs. Your speaker coils will burn out. That actually happened to me once at a gig. I connected the speakers, and half an hour later, I smelled burning, burn smells coming. And I realized, I had connected like I looked at the specs of the speakers, and then turned out it was a 4 ohm speaker connected to an 8 ohms amplifier. And so that's something you have to be very careful about. Your headphones, wired headphones, are typically 32 ohms. So again, that's a real life example of where we need resistance or impedance matching. Okay. The equation, there is a derivation for this, of course. There's a current flowing through here. I don't do the derivation for non-EE classes, but it turns out that maximum power is transferred when VTH square, when RL is equal to RTH, and the equation for PL max is given as VTH square over 4 times RTH. Okay. P, electrical power, is V square over R. R in this case is the sum of both RTH and RL. Okay, hence it is VTH square over 4 times RTH. Another common example is your vehicle battery, car battery. You ever hear that you had trouble starting the car during freezing temperatures? And the reason is a car battery is supposed to supply, let's say, whatever the voltage is. Motorcycle batteries are at 12 volts. Car batteries also should be around 12 volts. It's supposed to supply 12 volts at its terminals, but more importantly, it should be able to supply current, because the ignition coil requires a large amount of current for it to actually start up. And so a car battery spec has cold crank amps. It will specify a temperature at which it will supply a specific amount of current, cold crank amps. In cold weather, the electrochemical reactions inside the battery take place at a slower rate. So the battery voltage remains the same, but because the Thevenin resistance of the battery is now very high, a lot of that battery voltage is dropped inside the battery itself, and there's not enough voltage to supply to the ignition coil. And so Thevenin resistance increases at cold temperatures, and so our car has trouble starting out in the morning in very cold environments. So just real life examples. All right, that is the end of chapter 2. Any questions? Any questions at all?
I have a question.
Reminder.
Professor.
Yeah, go ahead.
You said you had a gig. What instrument do you play, and do you plan on playing it for the class?
No. That was a long time ago. I was a DJ. I used to play at parties.
All right, thank you.
It's a very long time ago. Since you're talking about music, I'll introduce some music next class. Next class is the quiz, but maybe on Wednesday. We'll look at some songs. Interesting segue. Quiz on Monday. I'll post the announcement later today. But again, I've been talking about this, all week long. It'll be Thevenin and Norton on Monday. I won't ask you to do a full analysis or calculation, only the problem setup. So students should absolutely be familiar with the topic and how to do the problem setup. Okay. I won't ask you to solve anything, but you should know how to present your work by doing the problem setup. All right. I will be available for office hours today. I'll be available over the weekend via email, via Zoom. If you need to see me, if you need to ask a question, again, send me an email. If if you need to meet me for a few minutes, that's also absolutely fine. Just get in touch with me, and we'll set up a time. All right, so I'll end class here today. I'll bid you a good weekend, and I will see you all on Monday.